Good call. You got my back. All right, so here we go. Chapter 3 homework, number 8. Okay, so here's what it says. Vector A, which is directed along an x-axis, is to be added to vector B, which has a magnitude of 7 meters. The sum is a third vector that is directed along the y-axis with a magnitude that is 3 times that of A. What is the magnitude of A? All right, so here's what we know. So we've got this vector A. It's directed along, I'm going to use vector notation here for a minute. So vector A is, it's directed along the x-axis. So how would I write that in vector notation? Well, let's just call it A times I. Follow?
Yeah.
All right, I never use, a couple people have asked about law of cosines. I would avoid it like the plague, personally. If you can make it work, rad, but I'm always skeptical. So skeptical, yeah. Yeah, exactly. All right, I will not make the joke that I was going to make. Okay, so here's vector A. Vector B. Vector B. What do we know about it? I just lost my spot. It's got a magnitude of 7. Ooh. So we've got. So have you guys learned in math class at all how to write the magnitude of a vector? So this is one way to do it, to just write the name of the vector but without the little vector hat. Okay? Sometimes people do this. Yes. That works too. Either of those two notation forms are cool.
Is that's how we're supposed to do that?
Sorry?
Yeah. That's what no.
Okay. All right. All right, and then it says the sum is a third vector, so let's call our third vector R, as in resultant. It's a vector that is directed along the y-axis with a magnitude of 3 times A. So if it's directed along the y-axis, that means that it's just 3A times J, right? Follow? Good? All right, so let's see if we can draw this. A drawing might help us. So I've got my vector A is pointing this way. It's got a magnitude of A. I've got some mysterious vector B that points off in some direction. And my result has to be this. So this must be vector B. Right? Do you guys agree that this is, that this is A plus B equals R?
Yes. Yeah.
Oh. So what does BX have to be? It's got to be negative A, right? Right? Can you see that? The X component of B is negative A, and the Y component is 3A. Does that make sense? All right, so here's what I know. I know that the magnitude of B, so this is, B is actually, what did we just say? Negative AI plus 3AJ. And I know that the magnitude is 7. So how am I going to use that to find out what A is? A squared plus B squared, right? So now I've got A squared plus 3A squared equals 7 squared, and solve for A. What?
Now I see.
Okay, Mr. Hacker, yeah, I understand that. I just didn't square the 3.
Okay.
So I did it right.
All right, so think about so a lot of this class, you guys, is going to be about problem solving. All right, last year, for the most part, everything that was on a test was just like a problem you'd seen on the homework. That's not going to be the case this year. It's impossible. Okay, there are too many permutations of different types of problems I can give you. There's no way I can show you everything. So you need, this class is almost more about problem solving than it is about physics. All right, so what was my problem solving strategy? I wrote down what I knew and tried to write it in sort of as concise a fashion as possible. And then looking at this, I was like, well, how the hell does that help me? So then I drew a picture. These are things you guys should be doing. Okay? make a picture that represents the problem. Okay? And in a lot of ways, the picture helped me more than this did in this problem, right? Good?
Yeah.
Questions on 8? Was that 8 that I just did?
Yeah.
Okay, 9. Am I going too fast? Cool. Somewhere I have a copy of the homework. I sat it down somewhere dumb.
I can give you mine.
Got it. Here we go, number 9. This one is similar. Oasis B is 25 kilometers due east of Oasis A. So here's Oasis A, 25 kilometers to Oasis B. Starting from Oasis A, a camel walks 24 kilometers in a direction 15 degrees south of east. Starting from Oasis A, a camel walks 24 kilometers in a direction 15 degrees south of east. So kind of this way. So here's my camel. 24 kilometers. This direction is, what did we just say? 15 degrees. And then walks 8 kilometers due north. Now, is my drawing accurate? Don't know. I don't know if this line should have crossed the horizontal line or not, because I don't know how far this is vertically. I could certainly figure it out though, right?
Yeah.
Then, how far is the camel from Oasis B? So, we need to figure out a way to write this as a vector addition problem, right? So, Peter, talk to me. What are you thinking?
So you kind of treat that inside triangle as like one being, and then so you have to figure. You could use like 24 sine 15 to find the segment of that 8-kilometer path that is like within the triangle. Or,
Yeah.
And then you can also find it to get the other side, and then you can find out like what those two additional vectors that are not in the triangle are, and then you can find the line, like the hypotenuse of that, and then that's how far you are from B.
Okay. Yes. I feel like we can streamline that process a little bit. All right. So there are 3 vectors here. Let me give these vectors names, and then I got you. Okay. So check it out. Let's give these vectors names. Let's call this vector. Oh, I can't use A, B, and C. Let's use X, Y, and Z. Great. Oh no, because then we'll have X components of X. I'm going to use R, S, and T. So whatever. Who cares? Here's R. Here's S. Here's T. What are we looking for? We want to know how far he is from here, right? So we're looking for that. We should give that a name too, right? So RST, we'll call that U. All right? So, Patrick. Sorry. I was like P. Oh, what do you, so give me an expression here. Or what were you thinking? Let's not even worry about components. Just tell me in terms of vectors.
Oh, vector S plus vector T plus vector U equals vector R.
Let's see, do I agree with that? Yes. S plus T plus U equals R. I'm cool with that. That's not the way I was thinking about it, but that totally works. S plus T plus U is vector R. S plus T plus U is vector R. Do you guys agree with that?
Yes. Yes.
So, and we know those vectors, so write them out in vector unit notation and solve for vector R, or for vector U. Cool?
Yep.
Is that enough?
How'd you do it?
I wrote it as, it boils down to the same thing. I wrote it as, so what vector U, the way we've drawn it here, is going to give us the distance the camel needs to walk to get to the oasis, right?
Yeah.
I interpreted it as how far from the oasis to the camel. So whatever, that's 6 of 1. So I did negative r plus s plus t equals u, but my u pointed the other direction from what you guys did. But it's the same idea.
Mine pointed you the generator.
All right, are we good?
Which part is R?
R is this vector going from A to B.
Okay. And T is the whole vector also.
T is the 8 kilometers north.
Cool.
Good?
Yep.
Everybody happy?
Yes.
Yes, Margaret.
Okay, quick question. If you have an answer that is like 0.1 off,
That's fine.
it's fine.
You 99% of the time, yeah.
Okay.
I mean, it depends. If the answer is 0.2 and you have 0.1, that's probably a problem.
Oh,
if the answer is 25 and you have 25.1, that's probably okay.
Okay, because on this one I got 22.5 instead of 2.6.
That's probably fine. Yeah, it's probably just a rounding issue. Okay, are we good? Questions, issues, concerns, anything? All right, number 10. Oh no, falling duck.
I thought that was R1 and I was so confused.
Number 10 is, I think, kind of the same idea. 2 beetles run across flat sand, starting at the same point. Beetle 1 runs 0.5 meters due east. Then 0.8 meters at 30 degrees north of due east. Beetle 2 also makes 2 runs. So everything that I drew in green is Beetle 1. Beetle 2, let's do in red. Anybody colorblind? Damn it. Can I do?
No, it's fine.
You sure?
Are
Yeah.
you colorblind?
Yeah.
What colors can't you see?
Red and
Maggie's
green, Holly?
colorblind. No, I'm not.
Red and green.
Like I can like tell the difference.
All right. Okay. Beetle 2 also makes 2 runs. The first is 1.6 miles at 40 degrees east of due north. So here's due north. 1.6 meters. Here's my 40 degrees. And then a second run. And we're looking for this, right?
Yes.
So, give these guys names. We need A plus B to equal C plus D. Write them out in vector unit notation and solve for vector D. Right? Does that make sense? It's A plus B. That's what Beetle 1 does. He's got to end up with the same result in vector as Beetle 2.
Yes.
Cool? Questions? Is that too hand wavy? Everybody good?
Yes.
All right. I'm going to move on then. Cool? All right. So, the other ones that were on our list, 6C is kind of more of the same. Oh, 6C, all you have to do is the Pythagorean theorem. You're given the vector. You know the x component's negative 140. You know the y component's 30. So just do Pythagorean theorem. Does that give you 143 though?
Yeah.
Yes.
Okay, great. And then 4B, if you found the magnitude of vector A, then finding the direction should just be some trig. So I think we got to move forward. If you struggled with any of these other ones, I'm around before and after school. Okay? Cool. All right. Notes. Damn it, why are my ducks all falling? Why am I swearing so much? Oh yeah, they're lonely. All right. So the rest of this chapter, you guys, is going to be about two-dimensional motion. All right? Because we're talking in 2 dimensions, very frequently we're going to need to use vector addition and subtraction. Okay? All right? So there's basically 3 chunks that we're going to learn about for for chapter 4. All right? The first chunk is going to be just a generic 2-dimensional motion section.
Bless you.
Bless you. All right, the first chunk is going to be a generic 2-dimensional motion section. Then we're going to do 2 worksheets on projectiles, which is obviously an example of 2-dimensional motion, right? Because I know we struggled with that last year and arguably didn't spend as much time on it as we should have. Weirdly, it's not in any of the curriculum, projectiles, which is weird. Like, yeah, like if you look at any like state physics curriculum, projectiles, nowhere in there. Yeah, weird, right? So we're gonna spend some time with projectiles, and then the last chunk is circular motion, which I think will be pretty easy. Okay? All right. So generic two-dimensional motion. So these notes, I wrote these notes up last year, kind of in a hurry. And this year I went through and edited some stuff and added some things. There's a lot of stuff that I didn't delete that we probably don't need. So some of these slides I'm going to kind of gloss through real quick. I will make sure that we hit on the important stuff, okay? So if I'm glossing through a slide and you're like, wait, what was that? I probably glossed over it because it's not super important, okay? Cool? Okay, cool. So, all right. So, because we are now talking about position, because we're talking about motion in 2 dimensions, so last year, anytime we talked about position, we talked about the position on a number line, right? So it made sense to say, oh, the position is 4, right? But now, because we're dealing with 2 or sometimes 3 dimensions, now we need to keep track of the position on the x-axis and the position on the y-axis, and then theoretically the position on the z-axis, right? So we are going to use the vector r to represent position. R as in radius from the origin is how you can think of that. Okay? All right? And that radius is going to have, for us, 2 components, but theoretically 3 components. There's an x component, a y component, and a z component. Cool? All right? We will, I think, in the homework, I don't think I used z components on anything. So I think everything is 2-dimensional. That's all you're expected to know for the AP test. So, but just know that doing a 3rd dimension is just more of the same. Okay? All right, so what this vector then is telling us is that my object is located at a position which is 3 meters to the left of the origin, 2 meters above the origin, and then 5 meters out of the page. Or whatever, however you set up your coordinates. Cool? All right, so change in position is exactly what you would expect. You're just subtracting the 2 vectors. Okay? Yeah, I think this is all fairly intuitive. So basically what this is saying is, if I've got R1, and then I've got R2, then this vector here represents my change in position. Right? Because then my initial plus my change equals my final. Right? R1 plus the change equals the final. Okay? And so what this expression is telling us is basically that it works either drawing it or component-wise. That if you find your change in x, that'll equal your resultant change in x. So, cool? Cool. All right. Okay, so let's do an example. All right, I think Dan randomly yesterday, which reminds me, I have papers to hand out. Remind me to pass these out. Dan mentioned parametric equations yesterday, and today we have to deal with parametric equations. All right, so here's the deal. On the last test, we dealt with writing position as a function of time, right? Okay, but that was just horizontal position. Well, now we've got 2 dimensions to deal with. We've also got a vertical position to deal with, right? So now we've got a vertical or a horizontal position that depends on time and a vertical position that depends on time. Since we've got 2 different things that depend on the same variable, that's a parametric equation, right? Cool? So I wrote up this example. So we've got a drone from Amazon. It's coming to my house to deliver my new pogo stick. I'm pretty excited to get it. So we're going to consider the Amazon warehouse as the origin. All right? We're going to measure time in hours. I hope I remember to do that all the way through this example. We're going to measure time in hours, and then the position is going to be measured in miles. Okay? So here's an expression for the position in miles as a function of time in hours. Here's the vertical position as a function of time in hours, position in miles. Cool? So we could, if we wanted to, and if we had the time, we could go through and figure out, by plugging in 0 for time, we could find the position of the warehouse. What are you going to get? 0, right? Because I told you that. All right, we could find the position after 0.2 hours or 0.4 hours just by plugging in 0.2 here and 0.2 here, or 0.4 here and 0.4 here, right? Good? I will spare you going through the calculations. Do you all agree we could do that without, it would be tedious, but it's easy, right? So there's what you get. Okay, so you get all these numbers.
Do we have to write these down?
They're in your packet. All right. Everybody good? Maggie, you good? You sure? Okay. All right. So now the question becomes, how do we graph this, right? Like in the past, we always dealt with position time graphs and velocity time graphs, but this gets ugly now, right? Because now I've got my horizontal position changing with time and my vertical position changing with time, right? Okay? So what we're going to do is the following. We're going to plot the points. So I'm going to plot this as a point. All right, and basically what we're going to do is we're going to plot the x, y position of the object at evenly spaced time intervals. Okay? So that's the coordinate 0, 0. That's where we are after 1 second, or hour, sorry. After 0.2 hours, here's my position. After 0.4 hours, here's my position, etc., right? So if you go through and plot those points, it gives you this graph that I've got at the bottom of the page. So here's my position at time 0, 0.2 seconds, 0.4, 0.6, 0.8. This would be 1 second. All right, now there's nothing magic here about 0.2. That's just what I chose to do in plotting this. Okay? So 1.2, 1.4, 1.6, 1.8, 2 seconds, we're right here. 2.2, 2.4, 6, 8, 10. 3 seconds, we're right here, etc. Cool? Well, I guess let's finish it. So let's see, 2, 4, 6, 8, 10, 4 seconds. Is that right? So here we're at 4.2 seconds? But that's not on the chart. Did I count wrong?
Yeah.
2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2. Huh. Look. Let's see. Huh. I don't know. There's a mistake in there somewhere. Something.
Something's fishy.
Lord.
Oh man, this is going to drive me bonkers. Does anybody see it?
3.8. 3.8 is next. No, 3.8 matches. It's the one in between 3.8 and what you think is 4.2.
Oops. This one?
Yeah, that's not
Oh, do I just have an extra dot?
Yeah.
Okay. So pretend that's not there. Oh, that would make sense because the dots are getting farther apart.
Right.
Okay, so this should be 4.0. Cool. Good eye. Thank you. All right, so I have an erroneous point. All right, so what this represents then is like if you were looking down on a map of Michigan, here's the warehouse. The drone took this weird path and it went to here, right?
Yep.
Cool?
Yep.
All right. Questions with it? All right. All right, now, average velocity and instantaneous velocity. It's the exact same thing we learned before, except you do it component-wise. So if you want to find the velocity in an instant, you take the derivative of the x position, that'll give you the x velocity. Take the derivative of the y position, that'll give you the y velocity. And now you can do the Pythagorean theorem to find that hypotenuse, or you can write it out in vector unit notation. Follow? Okay? So, average velocity is exactly what you'd expect it to be. It's displacement divided by time. Again, this is the only way to find average velocity unless your acceleration is constant. Okay? I still had one person do VF plus VI over 2 on the test. You can't do that if the acceleration is not constant. Cannot stress that enough. All right? I don't remember who it was. Okay, so to find average velocity, we're going to find the change in position. So you're basically going to subtract your two position vectors and then divide it by the time it took. Okay? So here's a silly example. I'll give you a better example. But so here we've got a particle moves through a displacement. It goes 12 meters horizontally, 3 meters vertically in 2 seconds. So to find your average velocity, you basically just say, okay, well, horizontally I went 12 meters in 2 seconds. Vertically I went 3 meters in 2 seconds. So my overall velocity is 6 meters a second. Oops. My overall velocity is 6 meters a second horizontally and 1.5 meters a second vertically. Cool? Oh, that's K, not J, but whatever.
So you can add the averages of each component's velocity and average those?
No, we're keeping them separate.
Oh, you just
I never averaged the X and the Y. I kept them separate the whole time.
Divided by the time. Okay. It just happens to be that it's 2 seconds.
Oh, I gotcha. Yeah, it's 2 seconds, not 2. Yes. Yeah. Clear? Everybody?
Now, let's say let's say there was an I, J, and K component. You would just do
Exactly. Exactly. Everybody good? Okay. All right. So now instantaneous velocity. There's a whole bunch of calculus here. I don't know that I want to spend a ton of time on it. Basically, you're finding the instantaneous velocity horizontally. You're finding the instantaneous velocity vertically by just taking derivatives, right?
Yeah.
Okay. The one thing I do like about what this little drawing shows us is, let me see if I can get this to let me embiggen this. Perfectly fraudulent words. Okay, so Zach asked about limits before. So if you look at this drawing, here's my object at one instant in time. Here's my object at another instant in time, right? So position 1, position 2, right? This little vector here is the displacement. Okay? So my average velocity between those 2 points points this way, right? Okay? Now remember, the whole idea behind calculus, the whole idea behind taking a limit is you make that time interval get smaller and smaller and smaller, right?
Yep.
So as I move point 2 closer to point 1, vector there going to get steeper and steeper and steeper.
Yes.
Okay? So what this vector here represents is it's called the tangent line, right? It represents the direction that the object is moving at that instant. Okay? This is important. I don't know that it's written out anywhere explicitly here. You might want to write this down. When you're looking at a map of the object's motion, okay, the tangent line at a point represents the direction of motion at that point. Okay? But only the direction. It doesn't tell us anything about, it doesn't immediately tell us anything about how fast you're going. It's just the direction you're moving in. So at this point, I know I'm going this way. Cool? But I don't know how long to draw that because I'm not differentiating here according to time or anything. You know what I mean? So, follow? Everybody good?
Yeah.
Is anybody on good? Hunter, you okay?
I'm good.
All right. All right. Oops. Oh, did I go too far? I did. Okay. Now, using calculus, you can differentiate to find the horizontal velocity, differentiate to find the vertical velocity, and that will then, using the Pythagorean theorem, then you can find the magnitude of the velocity at a point. Cool?
Yeah.
So let's run through an example of that. So this is all kind of what I just said, that you're finding your horizontal velocity by differentiating your horizontal position. Vertical velocity differentiates vertical position. Cool. All right, let's see. Figure shows a circular blah, 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 blah. All right, so let's take a second and do this. This is just kind of a quick concept-y thing to make sure you're cool with kind of what the unit vector notation stuff means. So it says the figure shows a circular path taken by a particle. So you've got a thing going around in a circle. It says the instantaneous velocity of the particle is 2I minus 2J, and then it wants to know what quadrant the particle's moving through if it's going clockwise. All right, so think about this. If it's going clockwise, in which of these three quadrants would it be if this is the velocity vector? So which way is this thing pointing? Let's see, 2I minus 2J. So 2I minus 2J, here's my velocity, right? So I need to find a point at which my velocity vector points along the tangent line, right? So let's see, if we're going clockwise, that's this way. So which quadrant would this velocity correspond to? Quadrant 1, right? It would be happening right there, right?
Okay.
Does that make sense, right? If you're going clockwise? So at that instant right there, it's actually going to be at 45 degrees. This is what your velocity vector would look like. Cool? All right. What if you're going counterclockwise? Then it'll be over here in quadrant 3, right? Because then you're going this way, so it would happen here.
Oh yeah.
So this is question A. This is question B. Cool or no?
Yeah.
Can you explain it one more time, please?
Yeah. So we know that we want to find this velocity vector, right? So in question A, you've got a thing that's going around in a circle. So it's going around and around and around, right? And so the question wants to know, where on the circle are you when this is your instantaneous velocity vector?
Yes.
So if you're going around this way, at this point, aren't you going that way?
Oh, it's an approximate. Okay.
Well, I mean, it turns out, because this is a circle, how do I say this? Your tangent line is always perpendicular to your radius. So since this is at a slope of, of 1, it's also going to happen, so that this has a slope of 1. I guess 1 and negative 1.
No, I know what you're saying. I couldn't figure out how you got it, and then I realized you were like approximating that one.
All right, are you good?
Yeah.
Is everybody good?
Yes.
Excelente! How are we doing on time? Not so great. Okay. Okay, so back to the drone. All right, so these are the same expressions I gave you before. We're trying to find the velocity now after 2 seconds. All right? So, let's do this. Here's my position as a function of time. So that means my horizontal velocity as a function of time is just dx dt. It's the derivative of the x, right? So take the derivative. What are you going to get? Negative 4.5 t squared plus 12t minus 4.5. I know I did that really quick, but it's just power rule, right?
Yep.
Okay? So that means then that Vx after 2 seconds is whatever you get when you plug 2 in here. So I will tell you that that is 1.5 meters a second. Questions on what I did there? Am I done? No. This just represents how fast the drone is moving horizontally along the x-axis at that instant. Follow?
Yes.
All right. Similarly, to find my vertical velocity, I'm going to differentiate my y position as a function of time. And so that gives me 6t minus, no it doesn't, 6t squared, sorry, minus 24t plus 16. And it turns out that your vertical velocity at time 0, at times 2 is 0. Follow? All right, great. So this sort of seems like tedious calculations, but we can make a little bit of sense of this. So what this is telling me is that at t equals 2 seconds, my velocity is 1.5 I meters a second, right? And there's no y component.
16.
Plug in. It's not
16, not
It
0.
shouldn't be 16 either. It should be -8.
Negative 8.
Yeah,
Okay.
not 0.
12.
Oh, I wonder if I put in 3 seconds.
Okay, irrelevant.
Okay, so you're telling me my answer is wrong.
Yes.
What is it?
-8.
Okay, sorry. Thank you for steering me back. You're right. Irrelevant. Shoot, I could have sworn. All right, maybe I made 2 mistakes. Okay, so are we good? So here's my velocity after 2 seconds written in unit vector notation. All right, so let's check and make sure that this makes sense.
Why are there vector hats here?
They should be vector hats. I'm just really sloppy about vector hats. It's one of those things that people know that it's there, but I've seen very few people who get worked up about it. Okay, so let's go back to our map of the drone's motion and look at where the drone is after 2, I keep saying seconds. These are not meters per second, they're miles per hour, aren't they? Miles per hour, sorry. All right, so all of this should have been miles per hour. All right, so let's see, after 2 seconds, 2 hours, dang it. All right, so after 2 hours, yeah, that makes sense. Because look, at that instant, the drone looks kind of like it's going this way, right? It's not going perfectly horizontal, it's not going perfectly vertical, it's kind of going mostly down, but a little bit of horizontal motion, right?
Yeah.
And what you guys said is exactly right. Our horizontal motion was 1.5, our vertical is -8, so that checks out. Right? There's more vertical motion than there is horizontal. Cool?
Yeah.
Questions on that? Everybody good?
Yes.
Cool. All right. So the next question wants us to know the average velocity for the first 2 seconds. Hours. Just, I'm going to keep saying seconds. In your head, just go, Mr. Hacker's an idiot, and switch it. All right, so now it wants the average velocity in the first 2 seconds. Is the acceleration here constant? No, because if I take a second derivative, I'm still going to have a t in there, right? So, V average is displacement over time, which represents my position at time 2 minus my position at time 0 divided by the time of 2 seconds. I wish I hadn't used 2 seconds. Hours, yes. Damn it. All right. So, we're totally tight on time here. But so, do you guys agree we can find the x and y coordinates after 2 seconds, right? Hours. We know our original coordinate was 0, right? So find those 2 positions and divide them by 2. Follow? So if you do that, here's what you get. And then I'll shut up because the bell's about to ring. So our position at 0 seconds is 0. Our position at 2 hours is 3I plus 0j miles. What's that? I got it right this time, yep. Okay, so that means that my change in R is 3I plus 0j minus 0.
Oh, okay, we're not there yet.
Cool? So then average velocity, oops, is delta R over t. So 3I miles divided by 2 hours is 1.5I miles per hour. I know the bell's about to ring. Write that down. I want to show you one thing. I'm not going to write anything, but I want to show you something. Cool?
Yeah.
All right, so let's go back to the map. What is my displacement in the first 2 hours? Oh, 1, 2, 3. Right? So this vector, which I am now drawing in blue, represents my displacement vector for those 2 hours. divide it by 2 hours, and that means we went 1.5 miles per hour. Good?
Yeah.
Questions? All right, so tomorrow we just got to do acceleration. How do you think we do acceleration? Take one more derivative.
But it's harder than that because you divide by dt again, right?
Sorry?
Don't you have to divide by dt again and also hand out those papers?
Oh, yeah. Don't you have to do what?
The second derivative of the metric function, you have to divide by dt again.
Yeah.
It's like some dx like
I mean, notationally, yes, but it's exactly what you would think it is. You just take a second derivative of your x function, take a second derivative of your y function, that'll give you your acceleration horizontally versus vertically.
oh.